Alright, in this video I'm going to talk about intermolecular forces and what effect they have on the physical properties of substances. So just a quick reminder here, if I have a substance like H2O that forms a dipole because the oxygen likes the electrons more than the hydrogen, so they become partially negative, and the hydrogen becomes partially positive, and that's what we call a polar covalent bond. So that right there is a polar covalent bond, an uneven sharing of those electrons. And that is a intramolecular force. That's a bond within the molecule. Then the other option here is our intramolecular force. So if we imagine another water molecule coming along with its partially negative end and its partial positive end, and that those two dipoles see each other in our dipole-dipole interaction between those two molecules, we call that a intermolecular bond or force. And that is in between different molecules. So, what effect is that going to have on a couple things? Well, we're going to talk about boiling point, and we're going to talk about melting point a little bit, and then we're going to talk about solubility. So the trend here is that the more intermolecular force you have, the higher the boiling point will be. If we think of these forces as the forces that allow molecules to stick to the same area or form a liquid where they all try and stay together as opposed to spreading out through the entire container, then the stronger the force is that's holding them together or keeping them in the same spot, the higher the temperature can get before they break free and fly all over the room. So we have a few substances here. We have CO2, NH3, and H2O. We've talked about all those substances a bit now. And we've got three boiling points. So which one goes with which? Well, first of all, as seen here, H2O has a strong dipole-dipole interaction. They're very polar, and so this intermolecular force is quite high. So then we're looking for the highest of the boiling points here. So this one would be water at 100 degrees Celsius. Then NH3, if you'll recall from a previous video, has a dipole as well. But this dipole is not very strong. First of all, the electronegativity difference between nitrogen and hydrogen isn't that high. But second of all, this shape, this pyramid, has a high amount of cancellation, so we get a partial negative because the nitrogen is more attractive to those electrons, and a partial positive, but it's just not, dipole is not as strong as in water, as there's more shape cancellation. This shape is just a little bit closer to being symmetric than this shape. And the polar covalent bond isn't as uneven. So what that means then is that this one is going to have a lower boiling point at -33. And that leaves us with CO2. Who does have a bond that's polar. These are polar covalent. But its linear shape is symmetric. So that cancels out any dipole that might have been formed. So here we have no dipole, and so we have a very low boiling point at minus 79 degrees. So that's how intramolecular force is related to boiling point. The higher the force, the higher the temperature before those molecules can get ripped apart into a gas. The same basic trend is true for melting points. However, the structure of the molecule matters a little bit more when it comes to melting points, because when we talk about freezing, it has to form a crystal lattice, and the shape of the molecule can be good for forming a crystal lattice or bad for forming a crystal lattice, and impurities can affect it more. So the same basic trend is true, that the higher the amount of intermolecular force, the higher the freezing point, but there are some complications there, and so it's safer to say that's true for boiling points, but it is also generally true for melting points. All right, one more kind of substance I want to take a quick peek at here with regard to this boiling point before I move off to the next thing. Just clear some space for myself here. All right, sorry about that delay. We're almost there. Just make sure I have enough space to write. Okay, the other type of material that we haven't really talked too much about here, but we're going to talk about here, are organic compounds. So compounds that are carbon and hydrogen based, and that won't have any dipoles because the electronegativity difference between carbon and hydrogen isn't enough to make polar bonds. So here we could have methane, and then ethane, propane. So these all have the same basic structure as each other, and none of them form dipoles. So how are we going to tell whose intermolecular force is the strongest here? Hold on, I'll just finish butane here. So the rule for organic materials, or materials that have no dipole, is that the larger the molecule, the higher the intermolecular force. There's something called London forces, and I'm going to do a separate video discussing exactly how they work. But the rule is, if there's no dipole, the bigger the molecule, the higher the intermolecular force. So what that means then is if I was going to rank these in terms of boiling points, they would go from the smallest to the largest. This one has the most intermolecular force, because it's the biggest, and so it would have the highest boiling point. And this one has the lowest intermolecular force. Because it's the smallest, and as a result, it would have the lowest boiling point. The same basic true is that's what I was saying before about melting points. So when you have no dipole, the thing that you're left to consider is the overall size of the molecule. The bigger the molecule, the bigger the intermolecular force. And then again, the bigger the intermolecular force, the higher the boiling point, or the more likely those atoms are going to be able to stick together. All right. Another property that are affected by intermolecular forces is solubility. Polar substances, or substances with a dipole is what I mean by there, and a nonpolar substance is a substance with no dipole, like the organic molecules that we were just talking about. Polar substances, and the rule for this is that like dissolves like. So polar substances dissolve other polar substances, and ionic crystals for that matter, and nonpolar substances like oil dissolve other nonpolar substances. So if we look at that, if we want to determine whether or not something would dissolve in water, we have to see that if its type of intermolecular force is the same as the type of the solvent or the thing it's dissolving in. So for ammonia, since it has a dipole, we would say it's polar and it dissolves in water. Sodium chloride, NaCl, or table salt, is an ionic substance. And so, yeah, it would dissolve in something that's polar or something that's sort of charged like it. So that would also dissolve in water. Gasoline, which is generally octane, which looks a lot like one of these molecules that we were just talking about, but instead of having 2 carbons like that one that I just showed you, the oct here tells you that it has 8 carbons. At any rate, it doesn't have polar bonds. It has a symmetric shape, so it's a non-polar molecule. And so it would dissolve well in oil. In the last one, ethanol, and I chose ethanol because it's particularly interesting. Ethanol looks like this. Ethanol has a part of it that looks like an organic molecule, so this part of it is non-polar. But then it has a little end of it that looks a lot like water, and so this end of it is polar. So this interesting substance dissolves in both oil and water. And so it makes a good substance to help those two things mix with each other. We might see this with something, the more common thing we might think of here is soap, where it's good at making oil dissolve into the water so that those oils can be washed away. So those are a couple, obviously not the only ones, but those are a couple of the properties of matter that depend on the intermolecular forces, and it gives you an idea of why these intermolecular forces are so important.